Okay, I think I'm back. Hello and welcome to the Daily Space. My name is Dr. Pamela Gay and I am your host for however long it takes us to get through all that is new and exciting in space and astronomy, by which I mean we won't run past half an hour because then I'm turning this channel over to the next show. I apologize for all of the random technical difficulties that may take place. I am having computer issues. I just won the Apple refurbished computer roulette, and there shall be a new refurbished computer arriving on Monday. So hopefully things will get better. So to try starting this all over again, hopefully with fewer issues. Hello and welcome to the Daily Space for June 22nd. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today we're going to do a quick rundown of all that is new in space and astronomy. It is an exceedingly slow news day, by which I mean there were 0 press releases. This means there were no papers getting published today that any institution felt was worthy of a press release. This is a sad news day, but it's a Friday, and who wants to put out a press release on a Friday? So what I'm going to do instead is highlight some of the things that are in the process of going on and tie into a press release from yesterday. So as you may have heard, a group of scientists at MIT, and I'm not going to try and switch to visuals because I don't want to curse this stream potentially. Yesterday, there was an announcement from MIT Lincoln Labs researchers that in quick reduction of the Kepler 2 latest data release, they were able to identify roughly 80 new planets. Now, the reason I say roughly is not all of these objects are confirmed. Not all of these objects are necessarily real. However, in reviewing the latest Kepler data release, they were able to, in record time, go through the data and identify planetary candidates. This is important for a number of reasons. First of all, it's excellent training for what we're going to be doing with the upcoming TESS mission, which is hopefully going to be providing us first light and first data sometime this month. It is also confirmation that we can keep getting better at how we process our data, and we have the chance to be able to, thanks to software, go through and recover planets from data from all the spacecraft that are up there in a timely manner. Now, timely actually matters when it comes to follow-up on planets. We have this little problem that our planet is going around the sun, and as we go around the sun, it turns out there's whole sections of the sky that, well, can't be seen the entire year because sometimes those areas of the sky only appear during daylight. Now, if we want to follow up on newly discovered objects, if we want to start pointing ground-based telescopes with amazing spectrographs at these worlds to measure the compositions of their atmospheres, to look for situations capable of supporting life, we need to have night when these objects are in the sky. When our satellites, when Kepler data, when TESS data coming in the future can be processed extraordinarily rapidly, it gives us the chance to follow up on spacecraft data fast enough that the objects being observed are still in our night sky and also are still close enough to their host star that hopefully we'll be able to get the kinds of measurements that allow us to see sunlight going through that world's atmosphere before that world disappears around its star. So we have 2 different things that we're worried about. We're worried about where is our planet Earth in relationship to our sun, and we're worried about where is that other planet out there in relation to its star. And with all of these circles within circles, or in this case, circles outside of circles and interfering with one another, rapid response is the only way to make sure that both planets are still lined up to allow needed follow-up observations to take place. So Larry is asking, what part of the sky is only visible in the daytime? Well, it varies with time of year. Right now, during the day, we have constellations like Orion, which are high in the sky during the winter, that are now high in the sky during daylight. We have constellations like Sagittarius that are up in the daylight during December and are available at night only now in the summer. So if you think of our constellations, the constellations that match the newspaper when you were born information don't always entirely work out for when you were born, but they do work out for when those objects are available during daylight. So if you were born in December constellations, those are the constellations that are up during daylight in December. If you were born in August constellations, those are the ones that are up during the day in August. Now, planets, like Paranor's bringing up, those critters move on their own. And I can't say there's any one season where they are more likely to be up or down, because when they appear in our sky varies from year to year. It's the reason that you end up having to buy a new sky almanac every year, and the Royal Astronomical Society of Canada produces one of the best. The RASC Observational Astronomy Handbook for each year is one of my favorite publications. And what these guides do is they tell you, when is the moon full? When is it new for the upcoming year? When are the meteor showers, which sometimes vary by a day or more? When are the planets in the sky? So yes, Canada actually is one of the world's leading astronomy nations. Let's face it, they have really long, dark nights in winter, and that can be inspiring to a kid who doesn't have a whole lot of daylight, but gets to enjoy truly dark skies. Now, we're right now in a truly golden era of planet discovery that is just starting. Starting in 1992, we began to find confirmed worlds orbiting distant stars. The first ones weren't planets like we know them. They were small blobs going round and round, pulsars that were detected by how they caused delays and advancement in the timing of the pulsar bursts as the planet and the pulsar went around one another, affecting at the smallest scales, which matter with pulsars, exactly where that pulsar was located relative to the planet. It wasn't until the mid-90s that we began to find planets around more regular stars, starting with the discovery of 51 Peg, which is a hot Jupiter located on an orbit smaller than Mercury's around a star not too different from our own sun. With that initial discovery, we brought in a new area of science, observational exoplanet science. And with this research, we were using some of the world's largest ground-based telescopes to measure the fine movement of stars that are triggered by having these large planets orbit them and change their center of mass. So as these giant planets orbit their stars, they're able to tug the star to and fro. And they only do this by a few meters per second, the velocity that it occurs at. And we have the capacity to measure that. So the initial planets were found the best way we knew how, by looking spectroscopically at the motions of stars. Now we're finding not a few stars a year, but not a few planets a year rather, but sometimes a few planets or more than a few planets a night as we observe the Kepler data. With Kepler, instead of looking for the stellar motions that we're seeing in spectra. We are instead looking for the slight dimming in a star's light that is caused by a planet going in front of the star. Now, with both of these techniques, we're limited in what kinds of planets we're able to detect. To see the center of mass of the star moving, we need to have the star with a planet passing more or less between us and the star, so that the gravity of the planet is able to pull the star closer to us, and then as it orbits, pull the star further away from us. We were completely unable to see any planets that might be orbiting in the plane of the sky, going round and round, causing the motions of the star to be also in the plane of the sky. Now, thanks to the Gaia mission, which is a European spacecraft capable of getting finer astrometric. This is measuring the positions of stars in the sky by getting some of the highest quality astrometric data we've ever had. We're going to start uncovering those planets that are otherwise invisible, that are orbiting in the plane of the sky, because Gaia, for the first time ever, has the resolution necessary to measure the star's small motions, up, down, left, right, as its center of mass moves around in the plane of the sky. This is going to be a completely new way for us of finding planets that we knew was possible. We just never before had the technology to do it. And in addition to finding planets this way, Gaia also has the ability and has already published papers on how it has the capacity to find planets through transiting method. So it's also looking at the same stars over and over and over, looking for their motions across the sky. And as it does this, it sometimes doesn't measure these motions. It sometimes instead measures the star appears to get fainter and get brighter as a planet passes in front of it and blocks out some of the light that otherwise would have hit Earth. And this brings us to TESS. TESS is a new spacecraft that is an international collaboration led by NASA, and it launched back in April. It's on a crazy orbit. It's on a highly elliptical orbit that will take it out near the moon and bring it back close to Earth. And in this orbit, it's able to get away from a lot of the confusion that Earth can add to its data set. But then it comes home for sending the data back. And what TESS is going to be able to do is, unlike Kepler, which looks at a set field of view on the sky over and over and over again, TESS is going to go, I'm looking at this nearby star, I'm looking at this nearby star, I'm looking at this nearby star. And Gaia and Kepler 2, the continuation of the Kepler mission, are allowing us to practice for what TESS is going to be doing. TESS's mission is to find planets that are near enough that we can do detailed spectroscopy to study their atmospheres. Our latest Kepler data release, coming from the folks at MIT that sent out their work with a press release yesterday, that process they used uncovered one planet that's already primely located only a few dozen light years away, so close and so bright that we can start to do this kind of measurement. Now, it's important that the stars be close and bright so that they generate enough light that when we take that light and we spread it from being the pinpoint light we receive from a star using a prism or a grism, when we spread it out into a complete rainbow so that we can see the fine structure of the absorption and emission lines of the elements in the star's atmosphere. When we spread that light out, we need there to be enough light that we can spread it out all the way and get at all the smallest molecular lines that will allow us to see what is the composition of that planet. If you're nearby, you're closer, the light is spread out less, more of it is received here at Earth. If you're far away, then no matter how bright you are, we're still going to get less of your light, and it's just harder to do the science. Now, I see the question asking a prism or we split light up in astronomy two different ways. We use prisms in some cases, which some of you may have as window decorations that spread rainbows all around your room when sunlight hits them just right. We also use what are called gratings. These you may have also experienced. They are in the rainbow glasses that you can get at certain novelty stores that allow you to look up at a light and see its light spread into a rainbow. Grisms, diffraction gratings, these are different ways of dividing the light up. Yes, so we have different ways of, sorry, there's a massive rainstorm hitting right now. These are different ways of dividing the light up into that rainbow of different colors being put into different specific places where we can observe them. When we spread the light out, it suddenly becomes possible for us to say, this line right here, this is due to hydrogen. We now know there's hydrogen, and that's kind of a given. Everything has hydrogen. This line over here, this is indicating there's things like molecular, I studied magnesium hydrides for a while. And we do take redshift of the objects into account when we're studying it, whether it be cosmological redshifts that we see in galaxies or redshifts and blue shifts just caused by stars orbiting through our own galaxy. As these stars orbit, we see them moving further, we see them getting closer, and all of these things combine to, allow us to measure what molecules and atoms are located in our universe. This allows us to see there are organic molecules, there are amino acids, there are polycyclic aromatic hydrocarbons. It's an exciting chemical-rich universe out there. And the question we now have is which of those elements are attributed to which planets? Now, TESS, which should finally be settled into near its final orbit, and I have to admit, I did some Googling this morning looking for updates, and I haven't really been able to find anything. It should be nearing its final orbit. It should be delivering first light data this month, and hopefully everything checks out A-OK. And in the not too distant future, TESS will begin to systematically look at nearby stars over and over and over again, looking to identify which of these stars have planets that we can do spectrographic follow-up on, and we can start to identify what is in the atmospheres of other stars. And this is where astrobiology starts to come into play. Through the study of astrobiology, folks have been working to figure out where are there different molecules indicative of life. There are certain chemicals that get destroyed in ultraviolet light. Methane is one of them. Methane, as far as we know, only has two sources. It can be generated through tectonic activity inside of a world, volcanism by a fancier term, and it can be generated through life. If we see a world that is rich in methane, we know that something has to be going on to generate that methane. Now, it may be tectonics. We look at Titan and we don't think that all of its methane comes from critters. But through astrobiology, there are all sorts of different collaborations of scientists working to define what molecules existing in an atmosphere could only be there through biological intervention, through an intelligent being, whether it be life as we know it or life as we don't know it, that are interfering with their atmosphere through their own industrial age. And what's exciting is all of this theoretical work that has been going on for the past 2 decades. This is a baby field. All of this theoretical research that's been going on for 20 years, all of the observational work that we have been building the technology to do with Gaia and TESS, and we have found ways to do even with a broken Kepler. This is all converging. And all these planets that we're finding are going to become targets for spectroscopic observations with James Webb and with currently existing optical telescopes here on the planet Earth. So this wasn't so much a, hey, look at these great things we've discovered. This was a, hey, yesterday MIT proved they have the data pipeline to say, we looked through the data, we looked through it quickly, and hopefully soon we're going to be able to use this pipeline we've developed to deal with the data coming down from TESS and figure out in weeks instead of months or years where the planets are so that we can quickly point our telescopes at them and find the places that just might be capable of supporting life. So that's what I had planned for today. I didn't leave as long as I wished for questions. I'm going to scan through quickly to see what I can do. Directly following this show, we are going to have Dr. Matt Richardson coming on. I'm afraid that Big J is still out sick, but he's going to be working on teaching you more of the science behind the news I discussed today. So Paranor has the last TESS tweet. I didn't think to look at their tweets. Update. TESS continues to operate in its science orbit that was reached in May. In one of the last passes, TESS performed a breakdance, rotating around to evaluate any stray light sources to characterize camera performance for the duration of the mission. Yeah, Big J is just suffering. He should be going back to the doctor. I don't think it's a secret he got shingles. This is one of those things that can happen to adults, and they apparently won't give us immunizations till we're 50. So being not that old, he was an unfortunate, yes, he had an unfortunate day, and we're going to sterilize his corner of the office now. So we're just waiting for him to recover. But we're going to have Dr. Matt coming and teaching you science. So scrolling back to catch the questions, I see Hanny asking, was methane the main gas in ancient Earth? I'm not sure it was the main gas, but there was a period in time where the life on Earth was dominated by methanogens. At that point, we didn't have the oxygen-rich atmosphere that we have today. And so methane-based instead of oxygen-based breathing, respirating life forms dominated our ecosystem. And it was only when we had a essentially burst of life forms that produce oxygen instead that our atmosphere flipped. And since methane breaks down naturally in ultraviolet light, as we began to get more and more critters, flora and fauna producing oxygen, they began to take up various ecological niches, outcompeted the methanogens, changed the characteristics of our atmosphere, and wrote the beginning of the story we're now living of being oxygen respirating life forms on an oxygen rich world. We do have a primarily nitrogen atmosphere, but the oxygen that's in it, it makes all the difference between living and dying. Looking to see if there's any other questions. Shingles is not related to the measles. It's a chickenpox virus. They may be in the same viral family. So yes, there was nitrogen way back when, but what I don't know is what was tied up in what particular way. The chemicals in our atmosphere, as they evolve, exactly what we can call dominant has changed. And I have to admit, I don't know those details. So rather than saying, yes, of course, nitrogen was definitely the dominant gas even then, I'm going to say I don't know. I simply know that methane dominated over molecular oxygen at that point. So are there any other questions unrelated to viruses? And I love the fact that you guys are so science knowledgeable that you can regularly stump me. So please keep asking me the hard questions because it encourages me to go out and learn more. And this helps all of us. What keeps all the nitrogen in the atmosphere? Gravity. Nitrogen is a fairly heavy molecule, and unlike hydrogen and helium that can easily undergo a collision with molecular oxygen and through transfer of momentum get accelerated to escape velocity, nitrogen's like, come at me. And you can knock the bejesus out of a nitrogen atom, and it's like, yeah, I've got mass. I'm not going to go that fast. I am not going to escape this atmosphere. So what we're looking at is at any given temperature, you're going to have a distribution of velocities of particles in the atmosphere. This distribution of velocities is what allows the zippier moving heavy molecules to hit all manner of tiny molecules, and through this transfer of momentum, this is the same thing of what happens when you're playing pool, where if you hit a ball just right, your cue ball will stop and the next ball will go hopefully rolling into a pocket, unless it's the 8 ball, of course. So this transfer of momentum works just the same with gas. But if you have, instead of two objects of roughly equal mass, thank you, keeper of maps, and I need to see what other things I've missed. If you have two things of unequal mass, it starts to become the story of, imagine, if you will, a toddler on roller skates and a sumo wrestler on roller skates. If that sumo wrestler rolls down a hill and collides with the toddler's going to go flying. If instead the toddler rolls down a hill, collides, and because they're rolling down a hill and we're assuming friction is constant for both of them, they will have the exact same velocity at the bottom of the hill, because acceleration doesn't care what your mass is as long as you ignore friction. So when that toddler rolls down a hill and collides with the sumo wrestler is like, yeah, kid, okay, I'm just going to pick you up. I might be moving slightly, but this is not exciting. This different in mass causes different outcomes with the collisions. So small atoms, small molecules get bumped to escape velocities, fly away. Bigger molecules are totally cool and like to hang out and are gravitationally bound to our planet. I don't know if you can hear it. There's a bird in my bird feeder behind me that is flinging seeds at the inside of the bird feeder. I apologize for any weird noises that may ensue. It may simply be distracting me and not be distracting you. So yeah, that's why we have nitrogen. So Larry, thank you for pointing out that I've already taught you the easy stuff. That's a huge compliment. Yeah, that's a great point, Larry. In university, people graduate and go away, but with those of you here on Twitch, over on YouTube with Astronomy Cast, and across all of our myriad podcasts, blogs, and live streams, you've been here for a long time. So Noel, the daily space is ending, but Dr. Matt's about to come on. So if you liked what you saw today, once again, this has been the Daily Space. We are a multi-institutional collaboration with Dr. Matt, who you'll see next, coming to you from the Planetary Science Institute. Annie Wilson, who's on this channel on Sundays, works in the planetarium at Youngstown State University. I'm Dr. Pamela Gay, and along with Dr. Andreas Plazas, we bring you the daily space and various office hours from the Astronomical Society of the Pacific. All of this programming is organized through the Astronomical Society of the Pacific, a nonprofit here in the United States. We do this because we want to put science in your brain, and we're glad you show up. If you want to make sure you get notified every time a new episode is going live, make sure to click that follow button. If you want to sustain our efforts, your subscription and every little bit really helps. So thank you for showing up. Thank you for bringing your questions, and thank you for learning. That gives us purpose for why we do all the things we do. Now, I'm going to hang up, and don't go away. We're simply transferring this stream down to Dr. Matt. I will be back on Monday with a new episode of The Daily Space at 1 p.m. Eastern. That's 6 p.m. London, 10 a.m. Pacific. I hope to see you all there. Have a fabulous morning, evening, afternoon, wherever you may be in the world. And remember to go outside and look up. Bye-bye.